Okay, trig limits in the squeeze theorem. Before we jump into that, I want to go back and revisit just a couple topics from the past, like earlier this week, last week. A couple things I want to just hit one more time. I was looking through our notes and I thought this would be worth doing. So what about something like this? Now, we looked at some examples where we were given graphs, but let's look at a piecewise function when we're not given a graph, when we have to evaluate the limit analytically. So here's a piecewise function, right? You guys are well familiar with piecewise functions. For each piece of the function, there's the function that defines the graph and the domain on which that piece exists, where it's defined. So we want to find this limit of this function, this piecewise function f of x as x approaches 2 if the limit exists. How would we do this? What do you think? This is a little different than the stuff we've been talking about, right? Because normally our first step is always just to evaluate directly, right? Well, how are you going to do that here? What do you think? Talk to me about this. Can we just plug 2 in? I mean, we can. The function is defined at 2, but in this case, just because the function exists when I plug in 2, and by the way, you just tell me real quick, what is f of 2? Four. How'd you get that? Okay, it goes into the bottom piece because 2 is in the domain of the bottom piece, right? Okay, give me thumbs on that. Does that make sense? Okay, so f of 2 is 4, but that doesn't mean that's the limit in this case, right? Because this piecewise function is knitted together. The two pieces meet at x equals 2, and we don't know if they meet at the same place. What are the conditions for a two-sided limit to exist? What has to be true for a two-sided limit to exist? By the limits, you mean the limits from the left and the right. Okay, have to exist and agree, right? If those limits, if the two separate one-sided limits don't agree, the two-sided limit is not defined, right? It doesn't exist. So we would have to check that. Now, to check the one-sided limits, how am I going to do that? Like, for example, how am I going to evaluate the limit of our function as x approaches 2 from the left? Which one do I have to use? The top one, yeah. Because this is the piece that's defined for values of x less than or left of 2, right? So this would equal the limit of f of x on this domain as x approaches 2 from the left. It's going to be there. What's that equal to? What's causing you trouble here? The negative sign? It's 7's the answer. Okay, but why were people hesitant about that or unsure? Is it because of that negative sign? Did that cause issues? Think what that negative sign means. It just prescribes a direction, but the value we're approaching is still what? 2, right? The value we're approaching is 2, and so when we're trying to evaluate this limit, this is just a regular looking limit, right? We're going to attempt direct evaluation and we got an answer, okay? Does that make sense? So that is the point clearly that the ant anticipates stepping on when we apply direct substitution for this green limit. It was a type 1, right? It was one where if the types are this, right? It was one of those. It worked. Okay, we got an answer. What about the limit from the right? What's that look like? The limit of what? Okay, that's going to be bottom piece, right? When x is approaching 2 from the right, that puts us in that domain. And so that's the function the ant is walking on, right? So we're taking the limit of 2x times the quantity x minus 1 as x approaches 2 from the right. And by direct substitution, what do we get? 4, right? 2 times the quantity 2 minus 1, which is 4. Okay, so then what is, if we combine those, the limit of my entire piecewise function, f of x, as x approaches 2 is what? Right? Because it doesn't agree. The two one-sided limits don't agree. They both exist, but they don't agree. So the two-sided limit doesn't exist. Okay, give me thumbs. How we doing? Okay, all right. Let's look at one more like this, slightly different. They give us another piecewise function with some parameters included, a and b. They want us to find values for a and b so that this limit of g of x exists and equals 7 as x approaches 2. Okay? How can I do that? They're telling me that the limit equals 7. By the limit, we mean two-sided limit, right? Okay. So we're two one-sided limits, right? Okay. So correct. Now, what's our motivation for that? How many unknowns are there in that piecewise function that we have to solve for? 3? What are the 3? 2? What are the 2? A and B. I need to find those values, right? So if I have 2 unknowns, how many equations am I going to need? How many relationships am I going to need to solve for 2 unknowns? You're going to need 2, right? Where do those come from? Well, the fact that the limit exists and it equals 7 implies that the one-sided limits must exist and agree. They must also equal 7. So we could say then that the limit of g of x as x approaches 2 from the left would be the limit of the purple part, right? The limit of a x squared minus 5 has to exist and equal 7, okay? Well, if I evaluate that directly, what do I get? What's the variable of the limit here? X is, right? So X is the value that we're going to be, that the limit is sensitive to. Everything else in there, in this case, the A, limit doesn't care about, right? So again, what am I going to get? As X approaches 2 from the left, if I evaluate this limit directly, what am I going to get? Everybody agree? Because I'm plugging 2 in for X, so I'm just going to get A times 2 squared, so 4A minus 5, okay? What's the limit of our function as x approaches 2 from the right. Well, which piece am I going to be using there? Bottom piece. Okay, so it can be that part. So I'm taking the limit of ax plus b. If I evaluate that directly, what do I get? 2a plus b. And we know that the limit is equal to 7. So both of the one-sided limits have to equal 7, right? There's my two equations and two unknowns. I should be able to solve this then. I could use, it'd be an easy system to solve. I'll just solve the top one first. If I solve for a, I'm just going to add 5 and divide by 4, so I get what? A equals 3. Everybody agree? If I know a is 3, I can use the bottom equation to solve for b. 2 times 3 is 6, plus b is 7. So b must equal 1. We got it. Okay, make sense? Okay, all right. So then for today, an extension of yesterday's stuff, we were looking at special trig limits. Okay, and we did this one, right? Did we finish this one? Yeah, we did. Okay, we did this one. Okay, let's look at something like, here, I'll just get rid of that page then from our notes. Let's look at one like this. This looks a little weird, but these are really common. The AP test just loves this kind of trig limit. Okay, so what can we do here? If I try to evaluate this thing directly right now, I get 0 over 0, which is undefined. It's indeterminate, right? Not undefined, indeterminate. Which of my special trig limits am I probably going to use here? First one, yeah. And we could maybe think about this one. So this is the one we're probably going to use. Let's maybe rewrite that slightly differently. It's just unfortunate that they both use x's here, right? Because that could be a little confusing. So let's rewrite it with a theta. The limit of sine theta over theta as theta approaches 0 is 1. There's our special trig limit, where theta is just the angle that the sine function is seeing. Okay, so in the problem we're looking at, what's my theta? What's the angle? What's building the angle that the sine function is getting, is being fed? For x, right? This is what we call the argument of the sine function. That's what's inside the sine function. So that's my theta, right? That's what's creating the angle. Okay, so do we have this pattern right now? Do I have the pattern sine theta over theta? So whatever's inside the sine function also has to appear in the denominator. I'm not quite there. I'm close. What needs to show up in the denominator? A 4. Okay, well, just think algebra here. What can I do? What can I always do algebraically? What can I multiply by to preserve the identity of any expression? What's the identity number for multiplication? 1. How could I creatively multiply by 1 to get a 4 on the bottom? 4 over 4? Everybody agree? So we could do this. What if I just multiply both the top and the bottom by 4? Look what we did, right? That works out great, doesn't it? Because now, look what we've got. On the bottom, we've got our theta. On the top, we've got a sine of theta. What's the only other piece here that doesn't quite match that pattern? Okay, well okay, true. But what else? Even with that 4, which we can deal with, there's one other piece that just doesn't quite fit that pattern. Oh, okay, it says x approaches 0, right? But let me ask you something. as x approaches 0, what does 4x approach? Yeah, right? Everybody get that? So seems a little weird, but we can freely just stick in a 4 there because that has to be true. As x approaches 0, 4x approaches 0. So that doesn't cost us a thing to do that, okay? And now, look, we've got everything we need except for, as you pointed out, what about that 4? Okay, there's a property of, and this is that second assignment deals with properties of limits. We have a limit property that we can use here. If I'm going to define the limit of f of x as x approaches some number a is L. Okay, what's the limit of some constant, which we'll call k, how about? What's the limit of k times f of x as x approaches a equal to? KL, yeah. Okay, what's the moral of the story there? The moral of the story is anytime we have a constant multiplier, we call this a scalar multiplier, or you could even call it a coefficient, as a part of a limit, I can pull constants that are being multiplied, coefficients, out in front of the limit. That's a step we do in calculus all the time. We always want to pull stuff out of the limit in this case. Later on, we'll pull constants out in front of derivatives or integrals. Okay? Because the limit of 4 times this function is the very same thing as saying 4 times the limit of the individual function, right? Okay, so then we do that and we end up with 4 times the limit of sine 4x over 4x as 4x goes to 0. Well, that looks pretty familiar, doesn't it? What is that limit equal to by our pattern? 1. How about that? So our final answer then is just equal to 4. Okay? See the trick? Again, we're just trying to extract this limit algebraically from what we started with using algebra. Okay? Let's look at another very similar example. Just make sure we get this stuff. So what about this one? It looks really simple. And by the way, there's that scalar multiple we were just talking about, right? Okay. So suggestions here. Walk me through some algebra. What's some stuff we can do? Can I pull the 4 out front? No, you're right. How come? How come, Tabor? You're say it again. Go ahead. How come? Okay, there's a 5 in the but how come I can't pull the 4 out in front of the limit? It's inside the sign. Exactly. So there are implied parentheses that we probably should write right there. The 4 is a part of the sine function, so we can't extract that. It's already inside another function. Is there anything we could pull out front? Okay, the 5 on the bottom, which means a 1/5 out front, right? Dividing by 5 is the same as multiplying by 1/5, agreed? That one's okay because that's not inside any function. That's just a coefficient, right? So we could do this. We could do 1/5 times the limit of sine 4x over x as x approaches 0 and play the same game we did before, right? What are we going to multiply top and bottom by to get our pattern that we want, our special pattern? By 4, exactly. So we'll multiply top and bottom, by 4. Look, now I've got a theta on the bottom. I can go ahead and put a 4 in front of the x. And I don't even really honestly need to, but a lot of times textbooks want that to match up with those two things. Okay, so easy to do. One last thing I've got to do, take the 4 out. Now I've got this other constant I'm stuck with that I'm going to pull out front with my 1/5. And so I end up with 4/5 times my special limit. And we know that this whole thing goes to 1, right? So what's our answer? 4/5. Okay, so we're just playing the same game over and over again. Okay, one more of those. What do you think? Take a second and look at that one. What am I going to do here? Suggestions. That doesn't really look like my pattern, does it? Again, my pattern, just to remind us, what's my pattern? Limit of sine x, I'll call it theta, over theta as theta approaches 0 equals 1. Okay, so there's my special limit. Somehow I've got to get one or more of those in this problem. It doesn't say anything about sine over sine though, so what do I need to do? Okay, what do you mean by remove it? How am I going to do that? Because I can't change anything. I can only rewrite it. Okay, well, you're kind of moving in the right direction, though. I need to separate those, don't I? Right? So I could write that quotient as a product. I could write that as the limit of, let's kind of separate these and make them color-coded. I've got the sine of 4x times 1 over sine of 5x, right? Okay, let me ask, there's a hint. Let me ask you something. If the limit of sine theta over theta as theta approaches 0 is 1, what's the limit of theta over sine theta as theta approaches 0? 1, right? 1 over 1 is 1. Okay? And if I wanted to, I could even write that, I could even write this argument as 1 over sine theta over theta, right? And then in the limit, I'm just going to get 1 over 1, which is still 1. Either way, those are kind of interchangeable, right? Because the limit, you see what I'm saying? I could write this as the reciprocal of that on the bottom, which looks normal. Okay, but we don't need to do that. We got both of those things. So in other words, it might be okay to build this pattern with the sine on the bottom and the theta on the top, which would be convenient for the blue one, wouldn't it? Okay, how am I going to make this work though? How am I going to make this work so I'm getting two versions of this pattern that are both going to converge on 1? Okay, we just got to do algebra. So what am I going to multiply top and bottom by here? What do you think? What am I missing for each of those patterns? What needs to go with the orange one on the bottom? What needs to go with the blue one on top? Okay, what do they have in common? They both have an x, right? So one thing I could do is I could just multiply through by x over x. Right? And I've just got a product of fractions here. So the top is just one big numerator, the bottom is just one big denominator. Ultimately, we'll separate these into two separate entities, right? But on top, I've just got sine 4x times x. On the bottom, I've got x times sine 5x. Okay, what else do I need for the orange one to work? 4. So what do I have to do? 4 over 4. Okay, so I'm going to put a 4 up there and a 4 down there. How about with the blue one? Okay, I need a 5. So I'm going to put a 5, multiply the top by 5 and the bottom by 5. And now this is starting to look pretty good, isn't it? Agreed? Okay, I've got a limit of, I could pull this 4/5 out front of the whole thing, right? Those are coefficients or constants. Questions? Right? So I could pull that out front. So I've got a 4/5 out front times the limit of oh, darn it. There we go. Right? Everybody agree? The limit as x approaches 0. But I can separate this into two separate limits, right? The limit of a product is equal to the product of the limits. So I could make this a separate orange limit and blue limit as x approaches 0, right? Agreed? The limit of orange times blue as x approaches 0 is the same thing as the limit of orange as x approaches 0 times the limit of blue as x approaches 0. Give me thumbs on that statement. Does that make sense? Okay. Ashton, does that make sense? Yeah. Okay. Okay, any questions? Okay, so I could, how is this changing then? So we get 4/5 times the orange limit. And in the orange limit, I'm going to let, as x goes to 0, so does 4x. Times the blue limit. And as x goes to 0, so does 5x. Okay, that looks pretty good because now, what's all that equal to? 4/5 times, what's the orange limit? 1. What's the blue limit? 1. So the whole thing just equals 4/5. How about that? Okay, make sense? They love that on the AP test. Do a few of those and get familiar with it, and you're just about guaranteed to see at least one of those on the AP test. Okay, so we'll come back, and you guys are going to do a problem set. You're going to have some questions on it. We'll come back and talk about those on the one where you're using these trig limits. Okay, I want to show you one last thing today. You know what? I'm gonna stop. I want to let you guys, because I kind of didn't give you those assignments when I meant to, give you a little time to work on those, get some questions answered. We'll do this tomorrow. This would be a good thing to end the week on.